Hi everyone. Well, I guess this will serve as our online review session. Unfortunately, the site that we run them through was down for maintenance today, so we weren't able to do it. This hasn't ever happened before. Hopefully, it won't happen again. But I apologize for you guys not being able to sit in on a live review session, instead having to watch this recorded one. So we didn't start at 2:30, and I guess we're not starting at 2 either. We're starting. Well, we're never starting. It's never going to be live. You'll just be stuck with this video. So sorry about that. I know that doesn't help people as much. Hopefully for the rest of the term, every other quarter or every other week, things will work out smoothly. But that said, for this review session, my plan, since I didn't receive any email questions, was just to kind of go through what I thought were the main topics on quiz 2 and 3. So those are the two quizzes that you got to have done this week by Sunday night? Maybe earlier, because there's some great football on Sunday, so you might want to get them done by Saturday night. So yeah, I flipped through them. I picked out the topics that I thought were the most difficult or the stuff that I could help people with, and I'm going over those. Hopefully these will match up with the things that you need help on. So let's start with some quiz 2 topics. As you flip through the material covered on quiz 2, it might seem like review. It should. The first few sections in this should feel like review. If it doesn't, that's okay. That's the purpose of going through it. And if it does, that's great. Just don't get a false sense of security. Some of the stuff will be new later on. So the first thing I want to talk about is multiplying polynomials. The acronym that most people think of when they're multiplying polynomials is FOIL. Stands for first, outside, inside, last. That actually only works if you're multiplying binomials. So something with 2 terms times something with 2 terms. Here I have something with 2 terms times something with 3 terms. So that acronym doesn't work anymore, but the idea still does. That you have to take each term from over here and multiply it by each term over here. So there's at least two different ways to do that. Some people just like to kind of, all right, x times 2x squared, and then x times negative 5x, and x times negative 3, and just kind of make sure they hit everything. I find it's easy to miss things if you do it that way. So the way I typically do things is with this little box method, where I take one of the polynomials, x plus 2, and I sort of write it vertically here, and then take the other polynomial, 2x squared minus 5x minus 3, and write it horizontally, and sort of create little boxes, kind of create a grid where each term in the polynomial gives us either a row or a column. And it's just a way of keeping everything organized. It's the exact same thing as if you tried to do FOIL, or the extension thereof. Anyways, what I'm going to write in this box, maybe I'll switch colors, is what x times 2x squared is. X times 2x squared is 2x cubed. X times negative 5x is negative 5x squared. X times negative 3 is negative 3x. 2 times 2x squared is 4x squared. 2 times negative 5x is negative 10x. And 2 times negative 3 is negative 6. If you have trouble understanding why any of these red numbers are what they are, let me know. But I kind of assume that you're good with that, so I'll skip past it. Now what you have to do is add up all of the red numbers. So I only have one term here that is third degree, this 2x cubed. So there's nothing I can add it to, but I can combine like terms here. I have negative 5 of these x squared things, and then I got 4 of these x squared things. So that nets out to negative 1 of these x squared things. And then I got negative 3x's and negative 10 more x's, so I got negative 13 of these x's, and then finally negative 6. In other words, when you multiply those two polynomials together, that's what you get. Down here, x plus 2 cubed. I did this problem because I believe your book does it a little bit differently. There is a formula to square, cube, raise to the 4th power, 5th power, any power you want of a binomial like this. It's a formula. If you have the formula memorized, you can plug in the numbers and get your answer. I don't like it. I don't like it because I don't like just memorizing things. If you have it memorized, that's great, but I think the work in memorizing the formula and plugging in all the numbers is just as hard as doing the problem kind of a more normal way. So a different way to do this, you should feel free to do it however the hell you want. If you want to do it using the formula, more power to you. I just want to present a different way. And my way is kind of thinking about what cubing something means. If you're cubing something, you're multiplying it by itself 3 times. A note that I want to make is this does not equal x cubed plus 8. You can't kind of distribute this cube down to each of your two terms. But when you're multiplying together 3 things, the way you multiply together 3 things is you multiply 2 of them together, and then take that thing and multiply it times the third one. What I'm saying is if I ask you what's 2 times 3 times 5, you could be like, well, 2 times 3 is 6. and 6 times 5 is 30. So 2 times 3 times 5 is 30. That's true. That same analog, that same idea works over here. X plus 2 times x plus 2, I can do that. Foil things, do boxes if you want, whatever the hell you want. X times x is x squared. X times 2 is 2x, but then 2 times x is also 2x. So I get 4x, and then 2 times 2 is 4. X plus 2 times x plus 2 is x squared plus 4x plus 4. But I'm not done because I still have to multiply by my third x plus 2. So now I got to multiply these two things together. Different ways to do it. I might revert back to this box method here. One of my polynomials is x plus 2. My other one is x squared minus 4x plus 4. And I'm going to write them in this grid just so that I don't lose anything. So I keep track of everything I'm supposed to multiply together, just to be careful. You don't have to do it this way. Just trying to help. X times x squared is x cubed. X times negative 4x is negative 4x squared. X times 4 is 4x. 2 times x squared is 2x squared. 2 times negative 4 is negative 8x. And 2 times 4 is 8. And so if you add up these 6 numbers, combining like terms where you can, you get this x cubed. I got 2 of these x squareds, and I got negative 4 of these x squareds. That nets out to negative 2 of these x squareds. Negative 8 plus 4 is negative 4x plus 8. Get this right here as my answer. There's a formulaic way to get straight from here to here. I'm not even going to bother. Well, no, I'm not going to bother. If you wanted to use the formula, let me know. I can show you the formula. But I don't think it saves you much time. And I don't think memorizing is a good way to do this kind of stuff. All right, moving on. We just spent some time multiplying polynomials. Another topic is dividing polynomials. There's at least 2 different ways to divide polynomials. Later on, your book will teach you this method called synthetic division, which you may have seen before. The downside with synthetic division is it doesn't work. It doesn't teach you, it doesn't work. Well, it doesn't always work. It doesn't give you a way to divide any 2 polynomials. It only works if the divisor, the denominator, the number in the bottom, is a linear term. X squared plus 3 is not linear. It's quadratic, so it doesn't work. However, there's this method called polynomial long division that does work. Now I'm going to demonstrate polynomial long division now. Before I do, I'm going to do long division. I'm going to do, 5 divided by 627. Because you probably haven't seen long division in a long time, but it might be easier to remember this before you do this. When you're doing long division, you kind of are trying to get rid of numbers from the left to the right. What I mean is you're not worrying about the whole 627. You're just worrying about this 6 right here, the furthest left thing. And you say, well, I can fit 1 5 in this 6, so you put a 1 up here. And then 1 times 5, you take whatever you put up top, multiply it by this, and write it down here. And then you subtract. 6 minus 5 is 1. And you can bring the rest of this stuff down, and then repeat that process. Now you're like, well, 5 won't go into 1, but I can look at the first 2 digits here, 12. 5 goes into 12, it goes in twice. 2 times 5 is 10. And if you subtract 12 minus 10, leaves me with 27. And then finally, 5 can't go into 2, but 5 can go into 27. It goes in 5 times. 5 times 5 is 25. You subtract, you get a 2. If you want a decimal answer, you can keep going. But for the purpose of having an analog to this thing, I'm going to stop here. And I'm going to say what that tells me is that 627 divided by 5 is equal to 125. Well, not just 125, because I also have this remainder of 2. So I have 2 more of these fifths. 125 plus 2 of these things out here. If that rings a bell, if that's familiar, it'll make this a lot easier to do. So when you're doing polynomial long division, the first thing I want to point out is if you're missing any terms, like note I have an x to the 4th term and an x cubed term, but then I jump all the way down to x, there's no x squared term. Put a placeholder in. Put in 0x squared. It'll make things easier for you. You don't have to do this. It'll make things nice. It'll make your columns line up well. That's why I put this 0x squared in here. And then just like you did over here, you're trying to get rid of things from the left to the right. So specifically, don't worry about all this stuff over here. You just want to get rid of 2x to the 4th. The way you get rid of 2x to the fourth is you write 2x squared up here. How did I know 2x squared? Because whatever you take up top, you're going to multiply by the thing out in front. So this 2x squared is going to get multiplied by x squared plus 3. And what that gives me is 2x to the fourth. Well, that's not 2x to the fourth. 2x to the fourth plus 6x squared. Sorry. 2x to the fourth plus 6x squared. Here's my x squared column way over here. And now when I subtract, like I subtracted here, I won't have anything left in this first column. Your goal in polynomial long division is to get rid of one column each time. Note that I wrote 6x squared over here in my x squared column, not in my x cubed column. I don't have anything x cubed because 2x squared times x squared plus 3 is 2x to the fourth plus 6x squared. If that makes sense, if you can subtract each of your columns now, you're done in a sense. You're just going to repeat that process over and over. So just like I subtracted here, 2x to the fourth minus 2x to the fourth, I have nothing. 3 minus nothing, I have this 3x cubed. 0 minus 6x squared leaves me with negative 6x squared. Careful, a lot of people mess up this sign. But remember, you're subtracting. 0 minus 6 is negative 6. And then x minus nothing, I'm just left with an x. Negative 4 minus nothing, I just get a negative 4. Where we are is we just got to this 127. This is our analog of the 127. If you get to this 127, you can do the rest of this stuff because you're just repeating the process over and over. That's what we're doing here. Repeat that process. You're not worried about any of this stuff. You just want to get rid of 3x cubed. If you want to get rid of 3x cubed, you better put a 3x up here. Why 3x? Because 3x times x squared gives me 3x cubed. And 3x times 3 gives me 9x. I'm going to put that in my x column and subtract. These go away. Negative 6x squared minus nothing is just negative 6x squared. 1x minus 9x is negative 8x. Again, be careful with the sign there. That'd be easy to write, I don't know, positive 10x here maybe. And then negative 4 minus nothing here. And then repeat. Continue to repeat until you can't put any of these in this thing. Continue to repeat until you get a number down here like 2 that's so small you can't put any 5s into it. So I can do this again. I want to get rid of negative 6x squared. Let's put a negative 6 here. Why negative 6? Because negative 6 times x squared gets me the desired negative 6x squared that goes right here. Negative 6 times 3 is negative 18. And again, I subtract. Again, note that this first column canceled out. Negative 6x squared minus negative 6x squared, that goes away completely. Negative 8 minus nothing, I get negative 8. And negative 4 minus negative 18, careful with that one. Sorry, that's negative 8x. Negative 4 minus negative 18 is the same as negative 4 plus 18, which is 14. This thing right here is so small that I can't continue this process, kind of like when I had the remainder here. So what I say is that when I divide these two polynomials, instead of saying I get 125 plus 2/5, I'll say I get 2x squared plus 3x minus 6. Right, that's the analog of the 125. Oh, and I got a little bit of a remainder. So instead of 2/5 is my remainder, I got negative 8x plus 14 divided by x squared plus 3 is my remainder. Right, I take the number down here that's my remainder, the 2, and I divide it by the number on the outside here, the 5. Sorry, that got kind of squeezed in, but that right there is your final answer. That's polynomial long division. Hopefully that makes sense. If you've seen it before, that was review. If you haven't seen it before, that was probably a little too fast to go through it, but hopefully it's at least helpful. Moving on, rational exponents. Very different topic than what we've looked at above, but that's kind of how these first few quizzes are, is they just throw a bunch of stuff at you because it's supposed to be review. They ask you to simplify 4 to the negative, what's that say, 3/2 power. So what this is doing is using a bunch of our exponent rules. The first rule that it's using is when you have a negative exponent, that just means take the reciprocal of. In other words, a to the negative x power is just 1 divided by a to the positive x power. What I'm getting at is 4 to the negative 3/2 is the exact same as 1 divided by 4 to the positive 3/2. It's using this first exponent rule here. The next thing you need to know is let's say a to the b divided by c, another exponent rule. What do you do when you have fractions? I got fractions over here. What the hell does that mean as an exponent? Well, what it means is just the cth root of a to the b power. I'm making that seem more complicated than it is. The thing on the bottom goes here, the thing on the top goes here. What am I talking about? Over here, 4 to the 3/2 power, we're just looking at the bottom here. The a is the 4, the b is 3, and the c is 2. So what I get is that this is the square root, right? The c is the 2, so there's a little 2 right here, of 4 to the 3rd power. When you have square roots, you don't even have to write the 2 here. If you don't write a number here, a 2 is implied. So what that is saying is this is 1 divided by the square root of whatever 4 cubed is. 4 cubed means 4 times 4 times 4. 4 times 4 is 16 times 4 is 64. So maybe I can squeeze an answer in here. So what I get for my final answer, the square root of 64 is saying what number times itself gives you 64. The answer to that question is 8. So my final answer is 1/8. That's right. You can do your problems this way. Works out fine as long as you got a calculator. The one issue is taking the square root of 64 isn't easy. I mean, you might know that the square root of 64 is 8, and that's great if you do. But if you don't, that step right there can be a little bit difficult. A way you can get around that is when we were at this step where we had the square root of 4 to the 3rd power, it turns out that you can rewrite this as the square root of 4 to the 3rd power. It turns out, using exponent rules, I won't get into why this works because hopefully you learned this in a different class. This is just supposed to be a review, that this is equal to this. And this might be easier to calculate. Let me show you. What I'm saying here is I need to figure out the square root of 4. Not the square root of 64, but the square root of 4. Square root of 4 is just 2. It's saying what number times itself gives me 4. That's just 2. And so what I got to do is figure out what that thing cubed is. 2 cubed, that's easy to do. That's just 2 times 2 times 2. That's 8. Another way you can get to the exact same answer is by switching the order that you do things in here, switching from this to this. Kind of a clever little trick. Often in math you can't switch order like that, but with these specific exponent rules, it works. Works out fine. So maybe I'll even say that you could also think about this as the cth root of a raised up to the b power. Little trick, you may not need to know that, but just one more thing that now you have that you can use if you want to. Moving on, rationalizing the denominator. Let's see, a little quick lecture on that. It turns out, if you put it into a calculator, that the square root of 2 divided by 2 is the exact same as 1 divided by the square root of 2. Try it. Put it into a calculator. Put this into a calculator and put this into a calculator. They're the exact same. Same answer. That might not seem like an issue, but that is a big issue in math. Because imagine you do a problem and you get this as your answer, and then you look at the solutions and I got this as my answer, and you're like, I guess I'm wrong, because they look very different. But you're not wrong. It's the exact same thing. It just looks different. So what mathematicians do is they're like, I don't want 2 different answers that look so different, so I better pick one of these 2 and call that form better. So if you get one of these 2, you're not done. You can simplify it, turn it into the other one, and then you'll know that's the right answer. We as mathematicians decided this one is good and this one is bad. I don't know. Sure. I don't think that helps at all. We decided this one's good. What's bad about this is we are never going to leave square roots, or really any roots, any radicals, in the denominator. And it turns out by enforcing that rule, we'll never end up with things that look like this. We'll instead end up with things that look like this. And now your answer will look like my answer, and we won't have that confusion. The process of changing this into this is what's called rationalizing the denominator. The way you rationalize the denominator is, first of all, on this specific problem, you recognize that the square root of a fraction is the same as the quotient of those 2 square roots. So the square root of 5/12 is the same as the square root of 5 divided by the square root of 12. I'm not too concerned about the square root of 5. It's totally fine to have square roots in the numerator. It's the square root of 12 that's causing trouble. So it's the square root of 12 I want to do something with. The trick to rationalizing the denominator is anytime I have a fraction, I can multiply the top and the top and the bottom of that fraction by any number I want, and I won't change its value. For example, if you have 1/2, you can multiply the top and the bottom by 3 and get 3/6. These are equal. You can multiply the top and the bottom by 100 and get this. All these fractions are the exact same. It doesn't change the value of the fraction if you're multiplying the same thing on the top and the bottom. That's the trick I'm going to do over here. But instead of multiplying the top and the bottom by 3 or by 100, I'm going to multiply the top and the bottom by the square root of 12. Why the square root of 12? Well, let me show you. When I'm multiplying fractions, I just multiply straight across. 1/2 times 3/5. I do 1 times 3 is 3, and 2 times 5 is 10. That's kind of the way you multiply fractions. So that's exactly what I'm going to do over here. Square root of 12 times the square root of 12 is the square root of 144, which is just 12. Square root of 5 times the square root of 12 is the square root of 60. What I now have is a fraction that doesn't have a square root in the denominator. It doesn't look like this original thing, but it doesn't have a square root in the denominator, which is a good thing. I've rationalized the denominator. I'm not done at this stage, but I'm done rationalizing the denominator. So the thing I want to teach you in this problem is to be able to go from this step to this step. As you'll see in later chapters, or maybe even in these chapters, I don't remember when you see it, is that this isn't simplified. The square root of 60 is not simplified. And the reason why is I can think about the square root of 60 is really just the square root of 4 times the square root of 15. Because 60 is 4 times 15. And the square root of 4 is just equal to 2. So really the square root of 60 I could write as 2 times the square root of 15. So I can say this is 2 root 15 divided by 12. Or I can take it a step further and say 12 is 2 times 6, and the 2 from there and the 2 from here cancel out, and I get the square root of 15 over 6 is my final answer. I was kind of hoping to teach you two separate things in this problem. That might not have been a good idea. Maybe I should have made it one where this is the final answer where this thing doesn't simplify. But to be clear, the rationalizing the denominator is done at this step. But then there's more simplification I can do over here. Let me show you another way to rationalize the denominator. When we started out, so here's a second way to do this same problem. Done this a few times, just showing you alternate methods so that you have more tools to apply as you like. We'll do the same thing. I'm going to say this is root 5 over root 12. However, now, before I rationalize the denominator, I'm going to simplify. 12 is 4 times 3. Maybe I do this over here. Therefore, the square root of 12 is the same as the square root of 4 times the square root of 3. But the square root of 4 is just 2. 12 sort of has this perfect square hidden inside of it. So I can rewrite it as 2 root 3. Now that I've simplified, I'm still not done. I haven't rationalized the denominator, right? You can't leave a square root in the denominator. But now instead of multiplying the top and the bottom by the square root of 12 to get rid of the square roots, I'll be multiplying the top and the bottom by the square root of 3 to get rid of my square roots. And the reason why is the square root of 3 times the square root of 3 is just 3. Square root of 9, which is 3. So what I'm left with on the bottom is 2 times 3, which is 6. And up top, I got root 15, which, note, is the exact same thing I got there. Order. Here's another example where the order you do things in doesn't matter. You can simplify the radical first and then rationalize, or you could rationalize and then simplify the radical. Totally up to you which method you do. Just wanted to show you two different ways to do a problem. More rationalizing. Honestly, I think rationalizing this problem is a little bit more complicated than we should be doing at this level of the class, but I saw this problem on the quiz and I kind of freaked out and I said, all right, I better do this in the review session because this is hard. What do you do when you have a square root in the denominator, kind of like we did up here, but you also have another term that's not a square root, so 1 in this case. This minus sign is what's making things so difficult. I have two terms in the denominator. You can try multiplying the top and the bottom by the square root of 2. It'll turn out that won't work. That'll get rid of this square root, but it'll introduce another one over here when you distribute everything through. Remember, our goal of rationalizing is getting rid of all of the square roots in the denominator. And the trick up here was just multiply by root 12 over root 12, or root 3 over root 3. Down here, that won't be the trick. Down here, when you have multiple terms in the denominator, what you want to do, the trick to it is multiplying the top and the bottom of the fraction, just like we did here, by what's called the conjugate of the denominator. What the conjugate of something is instead of something minus something, it becomes something plus something. The 1 stays the same, the square root of 2 stay the same. I just switched the sign in between them. Because this was minus, I made it plus. Had this been plus, I would have made it minus. It turns out that by multiplying by the conjugate, what will end up happening is all the square roots will go away. You shouldn't be able to see that right now that the square roots will go away, but trust me, they will. That'll always work when you multiply by the conjugate. I can't just multiply the bottom by the conjugate because then I'm changing the value of this fraction. You have to do the same thing to the top and the bottom so that you're not changing the value. Right? That was our example about 1/2 being the same as 3/6 because we multiplied the top and the bottom by 3. That's what I'm doing here. Multiply the top and the bottom by this weird conjugate looking thing. I want to show you why that works. Really, the magic is happening down in the denominator here. If you FOIL, if you think about this as a binomial and this is a binomial, 1 times 1 is just 1. 1 times the square root of 2 is just the square root of 2. 1 times negative square root of 2 is the negative square root of 2. And negative square root of 2 times positive square root of 2. Well, negative times a positive is a negative, so it's going to be minus something. Root 2 times root 2 is the square root of 4, which is just 2. And what maybe you've noticed is my positive square root and my negative square root, those two cancel each other out, and all I'm left is 1 minus 2, which is negative 1. That'll always happen when you multiply by the conjugate. We'll always get these square roots canceling out up here. Now I don't have any square roots in the denominator, so I'm in really good shape. Yeah, I guess I should simplify the top. The square root of 2 times 1 plus root 2, I'll have to distribute and get square root of 2 plus the square root of 2 times the square root of 2. But the square root of 4 is just 2. So I get root 2 plus 2 over negative 1. Typically, you don't like leaving a negative in the bottom of a fraction like this. You bring it out in front of the entire thing. And you don't have to write divided by 1. What I'm getting at is that is just equal to the negative of root 2 plus 2. Or, if you prefer, negative root 2 minus 2. Either of these are fine. I don't know which one's simpler. Realistically, I'm pretty happy even with this, because the point here is to rationalize the denominator, to get rid of the square root in the denominator. And we've done that at this step. But really, we should probably go all the way to here, because it looks weird to leave a negative 1 in the bottom. Good enough is a question I would be asking if this were a live review session, but it's not. So I guess I'm just moving on. That's the end of quiz 2, kind of. That's the end of my review for quiz 2. That's the end of some various topics that I thought it might help you to go over before you take quiz 2. Here's some topics that you might want to go over before you take quiz 3. I think the main thing you see in quiz 3 is a lot of factoring, specifically factoring polynomials. Factoring polynomials is kind of a meaty topic because there's a lot of different ways to do it depending on what you have. One case is just to look for the greatest common factor. Look at your 3 terms, the terms are the things that are separated by pluses and minuses, and see what they have in common. What I mean is 2 goes into 12, 2 goes into 6, and 2 goes into 8. So I can factor out a 2 from all 3 of these terms. Similarly, they all have an x to the... You know what? I'm going to write this out in more detail. You might not need this, but 12 is also 2 times 2 times 3. And x to the 4th is x times x times x times x. And y cubed is y times y times y. 6 is 2 times 3. And x squared is x times x. And then there's my y. And finally, 8 is 2 times 2 times 2. And x cubed. And y to the 5th. 1, 2, 3, 4. Shoot. 5. Good enough. And we're multiplying all these together. when you're trying to figure out the greatest common factor, these are called prime factorizations. I've broken these down as far as I can into multiplication problems. When I'm looking for the greatest common factor, I'm looking for what these things have in common. So you might be like, oh, they all have a 2? Yep, they sure do. So I can pull out a 2. And you're like, oh, what about another 2? I can't do that. This one has another 2 and this one has another 2, but this one doesn't. So they don't all have another 2 in common, so I can't pull out another 2. 3, here's a 3, here's a 3. Damn, no 3 over here. Can't pull out a 3 either. They all have an x in common. In fact, they all have 2 x's in common. But we can't pull out any more x's because this one doesn't have any more x's. Finally, they all have a y in common. But I can't pull out any more y's because this doesn't have any more y's left. So what I've pulled out is a 2 of these x's, and 1 of these y's. And what I'm left with over here is a 2, a 3, 2 of these x's, and 2 of these y's. And what I'm left with here, not a whole lot, right? Just a 3. And what I'm left with over here is a 2, another 2, looks like 1x, and how many y's? 1, 2, 3, 4 left over. 1, 2, 3, 4. This is what's called finding the greatest common factor. I've factored out the greatest common factor. Typically, you don't leave it in this ugly form right here. You say 2 times x times y can be written as 2x squared y. And 2 times 3 times x times y, I could say is 6x squared y squared. And I got that 3. And then I got 2 times x times y times y times y times y. In other words, 4xy to the 4th power. And so factoring out my greatest common factor brings me to this right here, which is my final answer. To be perfectly honest, you're typically not going to write it out in all this detail. You're going to get to the stage where you can just look at these guys and be like, yep, they all got a 2 in common, and they all got x squared in common and y in common. So I'll pull that out right here, and then just figure out what I'm left with in each of these terms. If it helps you to show all the work, show all the work. I don't care. Do whatever you want. Greatest common factor. The reason I want to do one of those greatest common factor ones first is because our next method, factoring by grouping, relies on that greatest common factor. You need to be able to do that in order to be able to do this. So greatest common factor, factoring by grouping. The way you do factoring by grouping is very similar, except now instead of looking for a greatest common factor between all 4 terms, just look for a greatest common factor make groups of them. So maybe I'll color code to make things more clear. Just take the first 2 terms and call that my first group, and take the next 2 terms, 8x cubed y to the 4th plus 4x to the 4th y squared, and call that my second group. And do this greatest common factor method, except instead of trying to take things out from all 4 terms, just take stuff out from the blue. So let's see, these guys got a 6 in common, an x in common, and a y in common. Their greatest common factor is 6xy. And if you pull out that 6xy, you're left with 2y squared over here. And if you pull out that 6xy over here, you're left with just a single x. When you're doing the factoring by grouping method, your goal is to be left with the same thing in the parentheses over here on the green side as I have in the parentheses over here on the blue side. So I'm hoping I can take something out, the greatest common factor from these 2 terms, and be left with the same thing in the parentheses. Let's try. Well, let's see, 8 and a 4, they got a 4 in common. X cubed, x to the 4th, each of them have at least 3 of these x's. Y to the 4th, y squared, each of them have at least 2 of these y's. So I can pull out 4x cubed y squared, and if I do that, see, if you take out 4x cubed y squared, you're left with 2. All my x's I took out, I got a y squared. And then if you pull out 4x cubed y squared from this one, you don't have a whole lot left. Took out all of these, all your x's except for 1, and both of your y's, and you're left with here. Note that when you're factoring by grouping, these parentheses should always be the same. If they're not the same, you made a mistake, or this problem won't factor by grouping. Should always work. Because the trick with factoring by grouping is now you're going to do that again, except think about it like you only have two terms. Here's one of your terms, here's your other term. So what you can do is you can take both of those terms have what's in the parentheses in common. So I can take that thing in the parentheses and I can factor that out in front. 2y squared plus x. If you do that, this is gone. I just factored it out. So all I have left is 6xy. And over here, this is gone. So all I have left is 4x cubed y squared. Factor by grouping, you get to something like this and you're all done. It's a little bit easier when you don't have x's and y's. It's a little bit tricky when you have x's and y's. The method is identical. It's just a little bit hard to keep finding these greatest common factors when you have x's and y's. But on the quiz, I think both types show up. So I figured I'll do the hard type and then the easier type. Hopefully you can handle those. Another method of factoring is when you have a quadratic trinomial. Sounds a lot worse than it is. All I'm saying is that you have three terms in your polynomial. And the degree of this polynomial, the largest exponent is a 2. Note that's the case in both C and D. Turns out that the way you do C and D is very different. The way you decide what type of problem you have is based on its leading coefficient. In other words, the number in front of the x squared. Here it's a 1, here it's not a 1. When it's just a 1, that's the good kind. Those are easy to do. When it's not a 1, it's the bad kind. Those are really hard to do. When you're factoring a quadratic trinomial whose leading coefficient is 1, all you need to do is find two numbers that add to the coefficient on your x term, -2 in this case, and multiply to your constant term, -15 in this case. There's a lot of numbers that add to -2, so I'm not going to worry about those. There's not that many that multiply to 15, or -15. 1 and -15, 3 and -5, 5 and -3, 15, -1. There's not that many. Go through your possibilities until you find two that add to -2. Let's see, I think -5 and +3 will do the trick. This times this is this plus this is this. Nice, these are my answers. When you're in the case that you have their leading coefficient equal to 1, all you have to do is put an x here and here, and then write these two numbers here and here. -5, +3. When you have a leading coefficient of 1, it'll always factor into this form, which you can find these two numbers. And you can kind of convince yourself why that works. If you FOIL this all back out together, the x times the x gives you the x squared, and the -5 times the +3 gives you the -15. So it was important that these two multiplied to -15. But if you think about your outside and your inside, I get -5x, and then I get +3x. So what I'm going to do is I'm going to add those two terms together, if you think about what you do when you're FOILing. So it's the -5 plus the +3, -5x plus +3x, that gives me this -2x. That's why I needed them to add to -2. Honestly, you don't need to know why it works. You just need to know that this method works when your leading coefficient is a 1. Get this answer, you're done. It's the good news. Bad news is when your leading coefficient is not a 1, things get harder. So here's one where the leading coefficient is not a 1. There's many different ways you can do this problem. There's a guess and check method where you just come over here and you write these and you sort of try putting in numbers to make it work. Well, let's see, I need a 6, so maybe this is a 3 and this is a 2, or maybe this is a 6 and a 1, and -6, and maybe this is that, and just start putting in numbers until it all works out. That method works fine. That's the way I learned how to do it, to be perfectly honest. The problem with that method is that it can be really troublesome when you're trying to take guesses and get things to work on a quiz. It's nice if there's a process that always works. I'm going to teach you the process that always works. The process is a multiple step process. It'll take a while. It takes longer than that guessing and checking thing if you can do the guessing and checking really well. But it doesn't involve any guessing and checking. First step. Similar to what we did up here, we want to find two numbers, but now it's different. We want them to add to not -15, not the constant term -6, but instead the product of the leading coefficient and the constant term. We want them to add to whatever 6 times -6 is. In this case, it's -36. Note that that's different. Up here, it was just this number, -15. Down here, it's 6 times -6 gives me -36. Damn, and I want them to multiply to that. I wrote the wrong thing. So just like up here, I wanted them to multiply to negative 15. Down here, I want them to multiply to negative 36. What these methods have in common is up here, I wanted them to add to negative 2. Same thing down here, I want them to add to positive 5. You want them to add to your middle term and multiply to the product of your leading coefficient in your constant term. Add to 5, multiply to negative 36. If you think about that for a while, you try to get two that work. I think plus 9 and negative 4 will be the ones that work in this case. If you have trouble finding these, start with the 36. List all the things that multiply to 36. And be like, well, if it has to be negative, one of them has to be negative, one of them has to be positive. And then start adding them up until you get two that add to positive 5. This is not your answer. We can't jump to the factored form here like we did up here. We instead go to step 2, where you replace your middle term, that positive 5x, with what you just figured out. So positive 9x and minus 4x. Take these things that you just figured out, put an x on them, and that's what you replace your 5x with. What I'm saying is let's change this from 6x squared plus 5x minus 6. Instead, let's call that 6x squared plus 9x minus 4x. What I did is instead of writing plus 5x, I wrote this stuff, minus 6. It's still not factored, right? It's not factored. I've just changed it into something that has, from something that has 3 terms into something that has 4 terms. The nice thing about these 4 terms is when you have 4 terms like that, you'll be able to factor by grouping. So if what I did up in part B made sense, that's exactly what we're going to do here. If part B didn't make sense, we'll watch it again, and maybe now it'll make more sense. My first group is these first 2 terms. Their greatest common factor is 3x. If I pull out a 3x, I'll be left with 2x plus 3. I just pulled out 3x from both of these terms. I need to be left with 2x plus 3 in the parentheses over here. In order to be left with 2x plus 3, I have to pull out a negative 2. Now I have the same thing in the parentheses, so I factor those parentheses out in front and see what I'm left with. Now this is gone and this is gone, so all I have left is this 3x and this minus 2. And that is your final answer. That is the thing that you can jump directly to at the start if you're good at the guess and check method. But I find that a lot of people don't like doing the guess and check method into the pressure of the test, so it might be worth learning this method here. All right, last page. I'm supposed to get out of here at 3. It's 2:53, so hopefully I can do this in 7 minutes. I don't know if I can or not, but let's see how it goes. Rational expressions, multiplying and dividing them. I'm going to show you how to multiply and divide them, then I'm going to show you how to add and subtract them. Wow, I got a lot to do. It's going to take more than 7 minutes. What you do when you're dealing with rational expressions, these fraction-looking things, is you treat them just like you treat fractions. Which is great if you know how to treat fractions. If you don't, I'm telling you what to do by telling you to do something you don't know how to do. But maybe I can review it a little bit. If I ask you to do 2/5 divided by 1/4, dividing fractions is difficult. However, we can change that into a multiplication problem by saying dividing is just like multiplying by the reciprocal. You take this thing on the bottom, this divisor, this quotient, I don't know what the hell the word is for this, the thing that you're dividing by, and you flip it upside down. And the reason you do that is now you don't have a division problem, which is hard. You have a multiplication problem, which is easy. That's what I'm going to do over here. I'm going to say, I don't want to divide these huge things. I don't really want to multiply them, to be honest, but I'd rather do that than divide them. So what I'm going to do is say this thing divided by this thing is equal to this thing times, not this thing, but the reciprocal of this thing. Change this problem into this problem. So if you start out with the multiplication problem, great, you're already here. If you start out with the division problem, change it into a multiplication problem. And now if I just tell you how to deal with the multiplication problem, we'll be done whether they start us with multiplication or division, because we can change division to multiplication. The way you do this, well, when you're multiplying fractions, 2/3 times 5/8, sure. There's 2 ways you can do it. One way is to multiply straight across and call this 10/24. That's not how I want you to do it. That's correct, but that's not how I want you to do it. The reason why is because this fraction, the numbers got really big, And I'm going to have to reduce this fraction, which is hard because 10 and 24 are such large numbers. 10 and 24 aren't that big, and I could reduce this to 5/12. But play along. Pretend these numbers got so big that you couldn't even reduce them. It would be nice if there was a way to jump straight from this over to 5/12 and not get these huge numbers in between. And there is. The way you do it is, instead of multiplying straight across, you first look to see if you can cancel any factors. I can cancel the 2 here with the 2 that's inside this 8 to make this an easier problem. Now I got 1 times 5 is 5, and 3 times 4 is 12. Right, I cut out this middle step. That's what we're going to do over here. So let me erase all that mess. I'm pretty good at multiplying polynomials, right? We did that in example 1, or the first thing I showed you for quiz 2, way up top. We multiply polynomials, even some pretty big ones. We did it. So I could multiply straight across. But the downside to doing that is I'm going to get this huge polynomial over here that I'll have to reduce, and it'll be hard to reduce it because it'll be so big. It'll be hard to factor things out. So instead, I'm going to look for things that I can cancel. It's hard to tell what you can cancel right now, but if you factor each of these 4 things, you'll be able to see what you can cancel. X squared minus 9 is a difference of squares. It factors to x plus 3 times x minus 3. X squared plus 2x plus 1, if I treat that like I did this problem, I need 2 numbers that multiply to 2 and add to 1. Sorry, multiply to 1 and add to 2. Those 2 numbers are x plus 1 and x plus 1, or I guess those 2 numbers are 1 and 1, so it factors to x plus 1 times x plus 1. Nothing I can do with this x plus 1 up here, I'll leave it alone. X squared plus 4x plus 3, that factors to x plus 3 times x plus 1. And now that it's written like this, it's a little bit easier to see what can cancel out. Just like I canceled out with my fractions, instead of multiplying straight across, I can cancel out this x plus 3. Maybe I need to switch colors. And this x plus 3. Cancel out this x plus 1 and this x plus 1. It looks like that's all I can do. So what I'm left with on the top is x minus 3. And what I'm left with on the bottom is x plus 1 times x plus 1. Or x plus 1 squared. If you leave it like this, that's great. If you'd prefer to FOIL this out and get x squared plus 2x plus 1, that's fine too. I don't care. Do whatever you want. You don't have to expand this out. You can leave it just like this. Either way is good. This divided by this is one of these guys. That's how you multiply and divide rational expressions. When you're adding and subtracting rational expressions, the bad news is it's harder. If I ask you what's 1/3 plus 1/2, that's hard. I can't just do 1 plus 1 and 3 plus 2. Kind of like with multiplication, I could just multiply straight across. With addition, I can't. You can only add fractions if you have a common denominator. So in this specific problem, I'll multiply this by 2 over 2 and this by 3 over 3 and change this into 2/6 plus 3/6, which is 5/6. That's essentially what I'm doing over here. I can only add or subtract these fraction-looking things that are called rational expressions if they have the same denominator. Maybe you'll get one on the quiz that has the same denominator. That's awesome. They're in good shape. Maybe you won't. If you don't, you got to make the denominators the same. In order to make the denominators the same, you have to figure out what's the least common multiple between these 2 denominators here. It's hard to tell the way it's written right now. However, if you factor x squared plus 4x plus 3 into its factors, x plus 3 and x plus 1, and you factor x squared minus 1 into its factors, x plus 1 times x minus 1, and you can figure out that the greatest common factor is x plus 3 times x plus 1 times x minus 1. So I need to, that's not the greatest common factor, that's the least common multiple. There we go, that's better. So that's what I need to make both of these denominators, x plus 3 times x plus 1 times x minus 1. This one's missing the x minus 1, so I'm going to multiply the top and the bottom of this fraction by x minus 1. Note that I do it to the top and the bottom, so I'm not changing any values. I'm kind of like my trick of 1/2 being the same as 3/6. That's what I'm doing over here. Over here, I'm missing an x plus 3, so I better multiply the top and the bottom by x plus 3. Now what I have is a mess. X times x minus 1 is x squared minus x. Sorry, I'm going to show this in more steps. I don't want to confuse people. Now that I have the same denominator, like if I asked you what's 7/8 minus 2/8, you'd say, well, just leave the 8 alone and do 7 minus 2. That's what I'm going to do here. I'm going to say this is x minus 1 times x minus x plus 3 times x plus 3. Subtract the two numerators. Leave the denominators alone. X minus 1, x plus 3, x plus 1. To subtract the numerators, I have to multiply everything back out. X times x minus 1 is x squared minus x. I took that x and I distributed it in. And then from that, I want to subtract x plus 3 times x plus 3 is x squared plus 6x plus 9. And be careful, you're subtracting this entire thing. So x squared minus x squared cancels out. Negative x minus 6x, negative x minus 6 more x's is negative 7x. And then minus 9 leaves me with this thing. If you really like multiplying out polynomials, you could multiply the three of these together, but you don't have to. Perfectly fine to leave it just like this. That's how you add and subtract rational expressions. In short, you find a common denominator, and the way you can see what the common denominator is by factoring. And then once you have the common denominator, you can add or subtract the numerators. Hard. Last example, complex rational expressions. I know how to divide fractions, right? I erased it up here, but I know how to do 1/9 divided by 4/5. I change it into multiplication and I do it. Bad news is I'm not asked to divide fractions here. I'm asked to divide a sum of two fractions by a sum of two fractions. There's 2 on the top and 2 on the bottom. If I could make it just 1 on the top and 1 on the bottom, I'd be in great shape. That's my goal. Make it 1 fraction divided by 1 fraction because I know how to divide fractions. The way you do that, just look up at the top here. I want to make this all 1 fraction. Well, if I want to add together these fractions, I keep saying fractions, they're rational expressions, but they look like fractions. I need a common denominator. The least common multiple between x and x squared is x squared. In other words, multiply this by x over x, and what you get is 4x over x squared plus 10 over x squared. Now that I have a common denominator, I can say that's 4x plus 10 over x squared. That's just the top. Do the same thing on the bottom. Least common multiple between x squared and x cubed is x cubed. To make this an x cubed, in this case it's x over x again. These won't always be the same, just in this problem it was. 2x over x cubed plus 5 over x cubed gives me 2x plus 5 over x cubed. Maybe the equals sign should be down here. This doesn't really look any better, but this is actually way better than this because it's now 1 fraction divided by 1 fraction. I know how to divide fractions. It's a lot like multiplying fractions, except I multiply by the reciprocal of the denominator. Flip this thing upside down. That gets me here. Multiplying rational expressions is a lot like what I did up here. Don't just multiply across, see if things will cancel out. Well, to see if they can cancel out, I have to factor. 4x plus 10 is the same as 2 times 2x plus 5. X cubed, nothing I can do with that. X squared, nothing I can do with that. 2x plus 5, nothing I can do with that, factoring wise. But now I got a bunch of stuff that cancels out. Switch colors. 2x plus 5, 2x plus 5. X squared gets rid of 2 of these, of the x cubed. It leaves me with just x. How about that? And so what I'm left with when all the dust settles is just 2x divided by 1 or 2x. This entire mess simplifies down to just 2x. And that's how you deal with complex rational expressions. That's the last topic that we got here. So I'll end this video here. Again, sorry for not having a live review session this week. Hopefully this is the only time that I have to send you a video like this. If there's any questions that I didn't get to that you really hope and ask me, just email me and I'll take care of it. Otherwise, I will make another one of these next week, and hopefully it'll be live next week. But that's the end of this video.